Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is Thevenin's Theorem as applied to AC circuits. We'll additionally briefly examine Norton's Theorem as applied to AC circuits. Our objective is to learn to simplify a complicated AC circuit into a Thevenin's equivalent. Ideally, the original and the Thevenin's equivalent will behave identical to each other. However, the Thevenin's equivalent circuit will be notably easier to build and to solve for desired electrical quantities. Bottom line up front. AC Thevenin's theorem is DC Thevenin's theorem with phasors. I cannot make it much simpler than that. This lecture therefore operates under the presumption the viewer has more than a passing familiarity with both Thevenin's theorem as applied to DC circuits and series parallel AC circuit analysis as illustrated in the DC Thevenin's theorem lecture and the Basic Electronics AC circuit analysis playlist, both available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. If you recall, Thevenin's theorem as applied to DC circuits rendered even the most tangled and gnarly of series parallel circuits into tame and docile pure series circuits that sit, stay, and roll over on command. The same is true for AC circuits, the one complication being that phasor equivalents and complex impedances are employed for analysis purposes. Thevenin's theorem is a two-step procedure that simplifies a complicated circuit to a simple series circuit consisting of a Thevenin's equivalent voltage source, ETH, in series with a Thevenin's equivalent impedance, ZTH, in series with our electrical load of interest, Z load. The original complicated circuit and the Thevenin's equivalent circuit should ideally behave the same, and importantly, the load impedance should be none the wiser to the substitution. Of note is not only the substantial ease with which calculations can be made for the range of load impedances using the Thevenin equivalent circuit. After all, it's a pure series circuit, but also how much less components, connections, and confusion is involved with the physical construction of the Thevenin equivalent circuit. Which would you rather be responsible for, a complicated series parallel circuit or a simple pure series circuit with only two elements? I know which one I'd prefer. As a demonstration of the utility of Thevenin's theorem, consider the following series parallel circuit consisting of a 120 volt 60 Hz AC voltage source and four elements: a 270 ohm resistor, a non-ideal 240 mH inductor that happens to have 10 ohms of internal resistance, a 6.8 microfarad capacitor, and a variable load impedance, Z load, currently set to 200 ohms at an angle of 20 degrees hooked in the following fashion. We're being asked to determine the anticipated voltage across the load, V load, and the current through the load, I load. Without the use of Thevenin's theorem, we need to resort to time-consuming series parallel circuit analysis. If you're up to the challenge, by all means, pause the lecture and try this on your own. Again, we're looking for the voltage across and the current through the single load impedance only, and nothing else. If you're tracking, you should have obtained the following results. The complex impedance of the 270 ohm resistor is 270 ohms at an angle of 0 degrees. Let's call this impedance Z1. Complex impedance of the resistive portion of the non-ideal inductor will be 10 ohms at an angle of 0 degrees. Let's call this impedance ZR. The complex impedance of the inductive portion of the non-ideal 240 mH inductor at an excitation frequency of 60 Hz will be 90.5 ohms at an angle of 90 degrees. Let's call this impedance ZL. The resistive and inductive portion of the non-ideal inductor are in series with one another. The non-ideal inductor therefore presents a complex impedance of 91 ohms at an angle of 83.7 degrees. Let's call this impedance Z2. Finally, the complex impedance of the 6.8 microfarad capacitor at an excitation frequency of 60 Hz is 390.1 ohms at an angle of negative 90 degrees. Let's call this impedance Z3. Before we start plugging additional numbers into our calculators, let's come up with a plan of attack. Often complicated series parallel circuits can be simplified into pure series or pure parallel equivalents, and then pure series or pure parallel properties can be applied to these simplifications. Once properties within these simplifications are solved for, all one needs to do is to map these properties back to the original series parallel circuit. A necessary first step for this procedure is to apply both Kirchhoff's current law and Kirchhoff's voltage law to the series parallel circuit in question to examine voltage and current distribution within it. Our Kirchhoff's current law analysis of this circuit illustrates that source current must travel through impedance element 1. Then it splits into two paths, a portion of which goes through impedance element Z3, and the other portion of which goes through the series combination of impedance element Z2 and our load impedance Z load. Let's call this path I single prime, where I single prime is the current through impedance element 2, which is also the current through our load impedance. Our Kirchhoff's current law equations demonstrates that source current equals current through impedance element 1, which equals the summation of I3 plus I single prime, where I single prime equals I2 equals I load. This KCL analysis implies that impedance element Z2 is in series with our load impedance Z load, a simplification I'm calling Z single prime. This additionally implies that combined impedance Z single prime is in parallel with impedance element Z3, a simplification I'm calling Z double prime. Our load impedance Z load is internal to Z single prime, which is in turn internal to Z double prime. Let's now examine voltage distribution within this circuit. A Kirchhoff's voltage law analysis of this first loop in red indicates that E equals V1 plus V2 plus voltage across our load impedance. A Kirchhoff's voltage law analysis of this second loop in orange indicates E equals V1 plus V3. Finally, a Kirchhoff's voltage law analysis of this third loop in yellow indicates V3 equals V2 plus voltage across our load impedance. These analyses again support our earlier conclusion that Z2 is in series with Z load, a simplification I'm calling Z single prime, and combined impedance Z single prime is in parallel with impedance element Z3, a simplification I'm calling Z double prime, where combined impedance Z double prime is in series with impedance element Z1. Again, our load impedance is internal to Z single prime, which is internal to Z double prime. Let's now perform an analysis of these much simpler circuits, then map these properties back to our original series parallel circuit. Z2 and Z load taken in series present a complex impedance of approximately 253.8 ohms at an angle of 38.8 degrees. Z3 and Z single prime taken in parallel present a complex impedance of 325.3 ohms at an angle of negative 1.8 degrees. There are several ways to obtain our desired figures. Perhaps the easiest and most direct means of doing so is through the use of two applications of the voltage divider rule, followed by subsequent Ohm's law analysis. An application of the voltage divider rule on our last simplification suggests that the voltage across combined impedance Z double prime equals 65.6 volts at an angle of negative 0.8 degrees. Given combined impedance Z double prime is the parallel combination of Z3 and Z single prime, it can be stated that V double prime equals V3, which equals V single prime. Voltage across elements in parallel is the same. Given combined impedance Z single prime is a series combination of Z2 and our load impedance Z load, we can now examine voltage distribution within this series branch. An application of the AC voltage divider rule suggests voltage across our load to be 51.7 volts at an angle of negative 19.6 degrees. Finally, Ohm's law suggests that current through Z load equals 258.3 milliamperes at an angle of negative 39.5 degrees. Without the use of Thevenin's theorem, this necessitated a lengthy series parallel circuit analysis. Despite the complications, we did solve for voltage across and the current through our load impedance. Or did we? I'm super sorry to say I just discovered an error in my previous calculations. Z load is supposed to be an impedance of 300 ohms at an angle of negative 15 degrees. Sorry about that. This means our earlier calculation for Z single prime is wrong, as is our calculation for Z double prime, as is our first voltage divider rule, our second voltage divider rule, and our application of Ohm's law. Hate to have to say this, but let's pause the lecture and recalculate all the values. Again, don't skip this step because it's vitally important to our later discussion. Wait a second. I do not know what's going on today. I'm totally hosing up this lecture. Z load isn't supposed to be 300 ohms at an angle of negative 15 degrees. I mean, Z load is supposed to be 300 ohms at an angle of positive 15 degrees. You can see the mistake, can't you? Go off and calculate these values. While you're at it, calculate the values for Z load at 100 ohms at an angle of negative 15 degrees, 300 ohms at an angle of negative 15 degrees, 300 ohms at an angle of positive 15 degrees, 195.9 ohms at an angle of negative 10.6 degrees, 195.9 ohms at an angle of 0 degrees, and 195.9 ohms at an angle of 10.6 degrees. I'll wait for you, and I'll wait a long time. Do you see the point I'm driving at? Every time Z load changes, you change the whole damn circuit, and it necessitates another complete series parallel circuit analysis. This is a serious drag, and there has got to be a better way. The better way is with Thevenin's theorem. Thevenin's theorem is a two-step procedure that simplifies a complicated circuit into a simple series circuit. The original complicated circuit and the Thevenin's equivalent should ideally behave the same, and importantly, the load impedance should be none the wiser to the substitution. Of note is not only the substantial ease with which calculations can be made using the Thevenin equivalent circuit, but also how much less components, connections, and confusion is involved with the physical construction of the Thevenin's equivalent circuit. The two steps in Thevenin's theorem necessitate a shift in perspective from the source to the load. Customarily, we've been performing circuit analysis as if the source is the one controlling the show. However, the source is really only part of the picture. Ohm's law supports this duality. Voltage influences current directly. Increased voltage magnitude, current magnitude increases. Impedance, however, influences current inversely. Decrease the impedance, current magnitude increases. Both partners are necessary for the dance. Thevenin's theorem takes advantage of this half of the equation. How does our variable load impedance see our circuit? The Thevenin's equivalent circuit consists of a single AC voltage source called ETH in series with a single impedance, ZTH, in series with our variable load impedance Z load. To simplify a complicated circuit into its Thevenin's equivalent, we need to solve for these two quantities, ETH and ZTH. Let's start by discussing the procedure necessary to solve for ETH, the Thevenin's equivalent voltage. First, one must remove the load impedance from the nodes of interest. Next, one simply determines the open circuit voltage seen across these two nodes of interest. Note the removal of the load impedance may fundamentally alter the nature of the original series parallel circuit, as we'll demonstrate in a moment. Solving for our Thevenin's equivalent impedance ZTH also necessitates removal of the load impedance. Additionally, one must also remove the source, or sources, from consideration. One removes a voltage source by replacing it with a short. One removes a current source by replacing it with an open. Make note that incorporating shorts and opens inside your original circuit may fundamentally alter the nature of your circuit, as we'll see in a moment. Finally, one determines the impedance of this modified circuit at the terminals of interest. Make note that ZTH is not the impedance seen by the original source. ZTH is the impedance seen at the load terminals of interest when the source has been removed. This shift in perspective may fundamentally alter the nature of this original circuit. Let's apply Thevenin's theorem to our original series parallel circuit. Let's first determine the Thevenin's equivalent voltage. Let's start by removing our variable load impedance Z load. Now we need to determine the open circuit voltage seen across these two nodes of interest. In this case, the removal of the load impedance prevents any current traveling through impedance Z2. All current will travel through the series combination of Z1 and Z3. Given no current travels through impedance Z2, there will be no voltage drop across it, and we can consider this circuit as a purely series arrangement of Z1 and Z3. By removing the load impedance, impedance Z2 has been effectively removed from consideration. The open circuit voltage of interest is therefore the voltage across impedance Z3, where impedance element Z1 is in series with Z3. Again, removal of the load impedance has fundamentally altered the nature of the original series parallel circuit. An application of the AC voltage divider rule solving for V3 yields 98.7 volts at an angle of negative 34.7 degrees. This is our Thevenin's equivalent voltage, ETH. Let's set these calculations aside and move on to solve for ZTH, the Thevenin's equivalent impedance.